Welcome to a lesson with Dr. Powell. We're going to talk a little bit about curvature. So if we take a curve in space and we look at the unit tangent vector, so it's tangent and it's 1 unit long, and as it moves along the curve, the only thing that changes if you look at this unit tangent vector here to here, and suppose that we've moved a distance of 1 unit length along the curve, so 1 unit length of arc length, 1 unit. If you want to think about this, think of the change of the unit tangent vector divided by the change of the arc length. Kind of approximates the idea of dt, where t is the unit tangent vector, dt ds. It approximates it, okay? So kind of in this picture. So we can have a picture approximation. So if you take where we were and we take where we are going, which is down here, and we take a difference from here minus that, we end up getting a vector here. This vector is divided by a unit length of 1. So this vector right here actually approximates the difference quotient, which approximates this. So this vector kind of corresponds to this idea of dt ds. So as we move along this curve, we have a derivative of how the unit tangent vector is changing with respect to arc length. Now, what if the unit tangent vector didn't change direction? So we were just going on the same line the whole time. Then, I mean, this picture, these two would line up and their difference would be 0 always. So the derivative would be 0, dt with respect to ds. Now, if we want to measure curving, how much we're curving, it's synonymous with how big this arrow is that we see here when we take a difference of 2 per one unit length, or in other words, the derivative. So the length of the derivative vector of the unit tangent vector with respect to arc length measures how much curving the curve or the path actually does. We call that the curvature. The curvature of a path is dt ds. How do we go about computing this? Well, we use the idea that ds dt, so movement, so along the path, is the same thing as the length of the velocity curve. These two things are synonymous and the same thing. And it allows us to move between derivatives with respect to t and with respect to s pretty easily. As follows: we have dt ds. We could multiply that by ds dt. Notice that kind of gives us a dt right here, right? And so we can think of this as being dt dt. We could also think of ds dt. We could switch this up a little bit and think dt ds and think of this as being that, and then dt ds, or s. That's an s right there. Okay, we could think of that. And this right here is the reciprocal of, so we could rewrite this as just ds dt, just put it in the denominator right there. Remember that this is simply just that. So we end up getting the length of velocity, and we end up getting dt dt. And if we're just finding, so dt dt divided by that is actually equal to dt ds. Since we're taking an absolute value or a length of the vector, we may as well just do that. And that's another way of thinking about how to find the curvature. Of course, we have to find t, and then we need to take a derivative of t. So a couple steps. Now, what is t? T is the velocity vector, but then you divide it by the velocity vector's length. It's to make it a unit vector. So you first find the velocity vector, divide it by its length, and then after you divide it by its length, then you take a derivative of that. And that derivative will be dt dt. Find that length and then divide it by the length of v of t. Notice that v of t can't really come out of here because it's not really constant. It is a scalar, but it does depend on t. So you have to take a derivative of it in this calculation. But if after finding these lengths, you can find the curvature. We'll talk in other videos about how to actually do this make this computation in other ways, but we also need an example, so that'll be coming up here shortly in another video. Thanks for watching.